Me to start.
Yes, please.
Good, thank you. So first of all, let me thank the organizing committee for inviting me to deliver the talk at this nice conference. I see the number of participants, it varies, but it is quite high, so it's really nice to see this. And what I will talk today, I'll talk about the recent progress in my research group, and in particular, will focus on the patterning of surfaces like implants with multilayer biopolymer microgels via hard templating using vaterite particles. So let me start. Yeah, now it works. Let me start from motivation, basically, why do we do this research? So you're all obviously familiar with biomaterials, which are plenty of different materials, including drug delivery systems, implants, scaffolds, and so on, which aim to support proper function of living organism or tissue growth. So maybe for some of you it may be a surprise, but for me once it was surprise that when I've seen the statistics that the majority, about 80% of all biomaterials, they fail after clinical trials. So huge investment from companies, and as soon as clinical trials, which are typically quite long, are over, so unfortunately it does not work. So, and the main reason is that currently used biomaterials, they lack the very important component that is present in nature, namely the dynamics in the cues, chemical, mechanical, and topological cues, which are present in the real extracellular matrix. So they can't mimic the real tissue and real material inside us very well. So this is why the main challenge is now the development of, this is already fourth generation of biomaterials, those that can offer a very high level of control over those cues in the space and time. And this is what basically we're focused on. And in my group, which is called Hybrid Active Biomaterials Group, HAB, we try to prepare different hybrid materials which we make active, so they can respond to particular stimuli on demand and change their properties where we want, when we want, and how we want. So basically we try to mimic nature in that way. And since these are hybrid materials, we make them from mechanically distinguished two kind of materials, hard and soft. And from those two combinations, hard and soft, you can get basically four different combinations. This is hard and soft in hard, soft and soft, and hard and hard. So no more other options. And today I will talk in the particular, this kind of hybrid materials, hard and soft. Here you can imagine this would be the coating or implants or something hard, which is coated on the surface with soft material in order to control the cellular adhesion, tissue growth, and so on. So example would be the coating of implants, but just to give you an idea that other kind of soft and hard material, this would be scaffolds with biofactors, hard scaffolds with soft biofactors inside. Soft and soft system would be what we can control at the interface between tissues, for instance, tissues with different properties, mass transport between tissues. Hard and hard example would be, this is what we are less involved, but working on this as well, would be the different nanostructured materials, which are primarily formed for detection. For instance, the nanoparticle-based materials for SERS, for surface-enhanced Raman spectroscopy. So today I'll focus on this hard and soft and mostly on the two-dimensional materials, but I'll give you some idea about the three-dimensional materials, how we can assemble them as well. So it was already at least one talk about the calcium carbonate vaterite particles, and maybe many of you are aware of those, and some of you, including myself, are in love with these particles. I call them my first love because I started to work with them a long time ago during my PhD study, actually. And just to remind you, for those who do not know, I will explain it a bit, some details for others, maybe to remind that I would believe that vaterite calcium carbonate particles or crystals, these are really excellent biomaterials due to different factors, which are basically I have mentioned here. So this material, vaterite calcium carbonate, this is one of the polymorph. There is also calcite, aragonite, and basically others. In nature, you can find vaterite. It is mostly calcite, but you can find vaterite as well as mineral, but also it can be extracted and prepared from waste material, so for sustainable synthesis. As the main properties that make this material really excellent, this is the porous structure of material. They are mesoporous, so pore size in the tens of nanometers. They're very inexpensive. If you don't want to extract them from nature but want to prepare in your lab, it will cost you almost nothing. These are biocompatible material and also biodegradable for some purposes. FDA approved, not only FDA, but since a while approved by FDA for drug delivery and many other applications as well. So what is very important, what I like very much, that the conditions to decompose calcium carbonate are very mild. This makes them applicable for fragile biomolecules, like many of biofactors and especially large biomacromolecules. So you can get rid of calcium carbonate at slightly acidic pH in the presence of EDTA, for instance, or citric acid or other chelating agents. So if you would, this is how they look like. Yeah, so some small particles with the porous particles, these are bigger particles. And if one would have a look to make a search on the applicability of vaterite crystals for drug delivery, you will see that over time, the number of publications and interest is growing and growing up. So right now, so typically the size of calcium carbonate particles that you can easily prepare in lab, this is size of some microns up to, let's say, 3 to 15 microns. This is conventional size range. But now we published rather recently, the paper how one can prepare such particles in lab in a simple procedure without any additives at all, making particles either huge, really giant, so you can see a single particle by your eyes actually, or very small in the nano is a sub-micrometer range. So basically they're already nanoparticles. And in all these cases, we don't use any additives, which is very good for multiple applications where it is hard to get rid of additives or any other additional components in the system. So as I mentioned already, they are porous, and porosity can be controlled as well. So if you prepare the particles at different temperature, which is still not that much different from ambient temperature, so you can get a control over the porosity of the particles that we have tested by the different biomolecules, in this case, fluorescently labeled protein as probes. So let me now come a bit closer to from this basically kind of overview and explanation why I love calcium carbonate, vaterite calcium carbonate, a bit closer to the main topic of my talk today. So I'll talk about how one can pattern the surface with microgels. So now we call these structures microgels, but maybe for many of you, you may still be familiar to know them as capsules. We try not to call them capsules anymore because they are not real capsules like hollow capsules, but they are more like microgels. So let me explain basically how this works. So you first synthesize calcium carbonate. That may be very simple synthesis by mixing of those two salts at specific conditions, concentration and stirring speed and so on. So you get the spherical calcium carbonate particle. And then you coat it with multilayers. I think most of you, or at least many of you who are now in the room, are familiar with the multilayer coating. But for those who are not familiar, let me just explain. You simply adsorb polyanion and polycation in the sequential manner on the surface and inside. In this case, they are porous particles inside and on the surface of particles. So first layer of polyanion, then polycation, polyanion, polycation. You just change positively and negatively charged polymer, just the sequence of them until the number of layers you wish is reached. So basically you introduce inside the pores of the particles, you introduce polymer complex and with different charges. Then at the next step, if you add, for instance, EDTA, you get rid of calcium carbonate and you will end up with basically inverted replica of those calcium carbonate particles, which will be what we call microgels. So now they are porous inside, and where you have the empty space inside, this was the space occupied previously by calcium carbonate. So here I call them freestanding microgels. This means that now you can't see here any surface. Everything is done as in the suspension of particles. Yeah, so they are not adherent to anything. We call them then freestanding. And this is a very classical approach how to make such structures. If they would be empty inside, they're typically called hollow capsules, multilayer capsules. But if they're fully fully filled with polymer to some extent. We call them microgels or matrix type capsules. Let me stick to microgel terminology. So what will happen if in the last step, when you get rid of the core, if you do it not in the bulk, but if you do it in the presence of solid surface, like implant, for instance. In this case, some particles, all of them, or maybe none of them, it depends, I'll show you this later on, may stick to the surface. And now they will be not freestanding FS, but will be SS, surface supported particles. This is the abbreviation for SS in this case. So they will stick to surface and you can actually hardly get rid of them. So this is what we have published a few years ago, that in the presence of solid surface, when you get rid of the calcium carbonate core, they may stick to surface during their formation, basically in one step. And then recently we asked ourselves what would happen if the whole procedure is done in the presence of surface. So this would correspond to this, underneath this slide, to this sequence of actions. And this was work done by a couple of master students. Actually, this was the master student thesis, and this was very successful. And what we found that everything like in the typical procedure, you can do in the presence of the surface, and then all steps will be done using the surface. All particles here will adhere to the surface. It's very easy to work with them. And finally, you will have not freestanding, but surface supported microgels. They stick to the surface. So today I will talk about this surface supported microgels, because this gives you a very unique opportunity. You can place them on the surface where you wish, either by control of the growth of particles here, or by the control of the location of this particle where you wish. And as soon as they stick to surface, they will be there forever. So this is a unique way just to organize particles on the surface, control roughness of the surface, number of particles, and so on. So this is what is called patterning of the surface, a very strong tool. So then we asked ourselves, why do they stick to the surface, basically? And still, I don't have the very good fundamental explanation of this, but I'll try to do my best today to explain what's happening there from fundamental point of view. But the full mechanism is, to my opinion, still unclear. If you know, if you would have any idea, let me know. That would be really helpful. So what we did, we have prepared to understand the mechanism of adherence or adhesion. We have prepared microgels using one polycation, this one, polylysin, and 3 different polyanions: hyaluronic acid, heparin sulfate, and alginic acid, or alginate. For 3 different polyanions, you can see here they're all polysaccharides, but they have different charge density. If you go down, so this is the highest, this is the lowest, so the charge density of them is varied. And what we found that, for instance, those microgels which are made from polylysin hyaluronic acid, they stick to the surface, and at the same time they shrunk during formation 3 times, but they stick very strongly. Other 2, so they stick to the surface. If you go to alginic acid, it sticks to the surface but does not shrink. So if you go to heparin sulfate and polylysin combination, it does not stick to the surface and does not shrink. So unless you heat up the system a bit, then it starts to stick and shrink about 2 times. So there is still a kind of mystery there, but some polymers which look very similar, biopolymers, they give with the same polycation, they give either sticky or non-sticky particles, so we can see black and white if you want. And what we found that we believe that the mechanism is depends on the balance between extrinsically compensated charge compensation in polymer complexes inside microgels and intrinsic compensation. So just to get an idea about the difference, extrinsic compensation is when the charges in the system are compensated by counterions, so added salt. And intrinsic is when 2 polymers interact with each other and compensate charges of each other by their own permanent charges on their own backbones. So I hope I explained it clear enough. So extrinsic and intrinsic charge compensation. A bit of teaching you about the interaction between polymers very briefly. So if 2 oppositely charged polymers, polyanion in this case and polycation, are interacting with each other, forming a complex, this is what's happening when you do multi-layer coating. We can consider this system from the position of double layer theory, which is basically the theory in physical chemistry that explains the redistribution of counterions from salt next to the charged solid surface. In this case, solid surface would be polyanion or polycation. And charges are really counterions are distributed around them according to double layer theory. And when two oppositely charged polymers interact with each other in the presence of salt, they form polymer complex, which is called in this case every plus and minus would form ion pair. So this is a polymer complex, and counterions are now released. Before they were bound to polymer backbone, now they are released. And release of counterions, this drives the entropic component in this physicochemical thermodynamics and interaction between the polymers. This is because this this is the contribution to this energy is coming from changes of enthalpy. Sorry, I mix up them sometimes. So delta A, change of the enthalpy, so energetical component, and delta S, change of the entropy. So basically the chaos in this case, in the system, in this case, whether the counterions are free or bound. So this is just a bit about the thermodynamics. This is what's happening when two oppositely charged polymers interact with each other. And in this interaction, concentration of salt plays a crucial role. If you add very little salt, here this is the ionic strands. So what you have the formation of polymer complex, but this is very defective. It's just one-way process. They don't go apart, and you can hardly control the interaction in this polymer complex. If you add too much salt, like here, more than, let's say, 2 mol per liter for this particular polymer pair, so then they don't interact, they go apart, basically. And if your concentration of salt is kind of optimal, which would be the specific range of concentration for each and every polymer pair, so then you will come into this equilibrium between extrinsically compensated charges and intrinsically compensated charges. And this will define the density in the polymer chain, the structure in the polymer chains, and this will result, hopefully, in so-called annealing. So polymers go from extrinsically to intrinsically compensated, force and back, finally can find the best combination in each other sterically, and this is what is called annealing, basically closure of the pores in the system when the system is becoming ideal. Ideally, they want to interact like that, one-to-one. So, and to better understand the mechanism inside from fundamental point of view, we have tested in our previous publication a couple of years ago 4 different polyanions and 4 different polycations. So I won't go much into details, but it was 16 different combinations of well-defined polymers when we tried to understand what's happening. And we found out that, again, for the same one of them can be used polylysine as polycation, and the range of 4 different polyanions with the increasing from top to down, increasing the charge density. You can see it from the schematics. If you go from top to down, there are more and more charge groups on the polymer backbone. This is a disaccharide unit. And what we found that if you increase charge density, this results in the decreasing the shrinkage of microgels, so they shrink less, and this results in the less adhesion as well. So adhesion and shrinkage of microgels, they work hand in hand. If they shrink, they will definitely adhere. If they don't shrink, there is a high chance they won't adhere. So here you can see some images of this. So here in this table, you can see those polyanions that have been used, and shrinkage coefficient goes from quite high and down to rather low, and adherence also very high for highly shrinked microgels, and 0 adherence for microgels which nearly show no shrinkage. And this is in inverse correlation with the charge density on polymer backbone. So we do believe that here, if there is stronger shrinkage, this is driven by annealing, and polymer can find the best spherical combination. This would compensate all possible charges or maximum of charges, and then if it's happening next to the solid surface, then not only electrostatic interaction, but hydrophobic interaction and maybe other short-range interactions are coming into play, and then it sticks, and it's really hard to get rid of. We did not succeed to get rid of at very harsh conditions unless you want to mechanically scratch out. So just some interesting observation. If you increase the polymer chain, In this case, we just used polylysine of 28 on average or 280 kilodalton. So if you make the polymer longer, then it suppresses both the shrinkage and adhesion. So again, this works this corroborates with our explanation of the polymer chain dynamic as the main driving force that defines the shrinkage and adhesion as well. So we have tested those microgel surface supported, or if you want sticky, we sometimes call them sticky microgels, as the vectors or drug delivery carriers that can not only host the bioactive molecules. In this case, we use dextrane labeled with fluorescently labeled dextrane as the model macromolecule, but which can release these model macromolecules in the presence of enzymes. So basically, biodegradation is the mechanism of release which is present in our body. And what we found out that if the microgels are shrinking more, you can see this from this graph. For instance, HA-based system is the most shrinkable and most adherent system. They degrade much less. So this again may be explained by our mechanism of shrinkage and mechanism of adherence, that if they shrink more, there is less pores in the system, they are more compact, and then it is more hard for enzyme to go through this system and to cut into pieces the polymers and induce biodegradation. So this is in line with our mechanism. So just to show you some ideas that one can pattern the surface not only in 2D but to make it in 3D. This is still unpublished, but I would like to share with you anyway because I found it quite exciting. So if you pack calcium carbonate particles not on the surface but in 3D, so just pack them in 3 dimensions like in a channel using microfluidics, for instance, then you can coat them in microfluidics as well, which is very easy with multilayers. And when you get rid of the calcium carbonate, you will have these capsules or microgels, depending, you can call them differently depending on their structure, which interact from each other in 3D. And again, for instance, if you take some microgels which show strong shrinkage, like polylysine hyaluronic acid that I've shown you before, so they never form stable 3-dimensional structures because they start just to fuse. They are more like fluent polymer network, and they never form a stable structure. So opposite to this, polylysine alginate, little change in the chemistry between alginate and hyaluronic acid, and this is huge in the stability of projects for very nice dimensional structures. So here basically did pattern 3D, if you want, by changing of the size of these calcium carbonate particles. One can also change the pores between these spherical objects as well. And if you encapsulate inside, in this case it was again dextrane inside, and here we form the real capsule, so they have no matrix inside but shell made out of multi-layers, which is well-defined shell. And by the assessment of the release kinetics of dextrane outside of the shell, we have been able to extract, using the analytical solution for 3-dimensional release, we have been able to extract permeability coefficient for such multilayers, and this helps to understand basically how these scaffolds, 3-dimensional scaffolds, can serve as the scaffolds for tissue engineering, for instance. Yeah, I think this was the last slide. So, and well, like, of course, it was only my name in the beginning, but of course, job was done by my research group and those guys who are present here. Yeah, thanks to them for this nice job. And if any questions, happy to